All right, number of challenges in this problem, right? So it's just figuring out the units. So a Pascal is a Newton per millimeter or meter squared. That's a Pascal. So the 250 or 207, I wrote the wrong number down, 207, can be written like this, 207 e to the 6, that gets rid of the mega, and then Pascal's Newton per meter squared. That's the way I remember it. So that's the way I do it. So then that gets put in with newtons per meter squared. Problem is we have kilonewtons on top, newtons down below. So if we end up with newtons per meter squared as our unit, then we have a Pascal. So that's one way to go about it. The other way we just researched out is 1 megapascal equals a Newton per millimeter squared. So 1 megapascal. So you can leave it in millimeters squared if you want, and then try to get it to newtons. So that's what I'm going to do, is go for this, which is a megapascal. That means I can leave that alone, because it's millimeters. I can leave that alone. The only one I have to get rid of is this. And there's 1,000 millimeters per meter. And if I want it squared, then I have to square everything. And it's still in the denominator where I'm doing this. Then that crosses. So now I have millimeters squared, millimeters to the 4th, newtons down here, right? Kilonewtons up here. So that means I need to get rid of this kilonewton. And that is a factor of 1,000 newtons, whoops, you know, 0 per kilonewton, and then that crosses.
This is deflection, right?
This is definitely deflection. Yes.
Subtle, yeah.
Yep, that's what this symbol is. And where'd we get this? Back of the book, yep. Where'd we get this? How do we know it?
Material.
Material, yep, it's material property, yep. And where'd we get that? I.
Very
Back of the book. How do we know which formula to use? All good finals questions. Yeah, there's some like just basic conceptual questions. Like, what is a material property?
Back of the book.
Well, I don't know about that for the answer. What is a shape property? Tell me a shape property.
The
What about a circle?
the moment of inertia.
Moment of inertia is a property of shape. What else about a circle? Area. Area of a circle, that's a property of the shape. What about the location of the neutral axis? Property of shape, not the material, right? Yeah, so all good finals questions. All right. Then we just crunch it, right? Once we have all the units working out right, and we get what? 1.5, I hear. Is that what you got? Yeah.
With some extra.
No. I'll see what I get. Oh, man. Yikes. Oh, no. My calculator's losing its mind. Oh, here we go.
This is 3 kilonewtons turned into 3,000.
Yep. Oh, now you make me start over because you talked to me. 1.5. What'd you do differently?
I just put 3,000 meters or 3,000 newtons
So that's,
Multiply.
yeah, so that's the same.
by 800 millimeters. Cubic. And then in the denominator, I put 48. Multiply by
207
by E,
by 8.
by E, by the E value for steel. And then multiply the I value.
What, if you, did you use 207 or what did you?
Yeah, I
use?
used 207.
But that's in what? It's 207,000 megapascals.
Yeah, and I put the times 10 to the 3.
So you're in
207,000 megapascals.
megapascals. Mega's also times 10 to the 6.
Yeah, but I used megapascals.
So you just left this in megapascals.
Yeah, I just left it in megapascal.
And above you have. I'm not sure that's gonna cancel with anything. You don't have megapascals anywhere else.
I have the same equation as you did at work. You just retype it in. It's fine.
Maybe it's just a calculator.
It probably is. This is a very busy equation.
Very simple load.
I know, it's about the simplest beam you can get. But the deflection is like terrible. And everyone gets that, right? Simple beam means supports at the end.
Yeah.
Yeah. She gets it.
Obviously.
She gets it now.
Yep.
All right, I'm gonna start to draw the second one. Do we need to do the second one, number 9?
Here, I put it in. Exactly. Probably.
Probably yes.
Make sure.
So it looks like number 9.
Can I just show you my like paper and my calculator?
No,
No.
No.
you can after class, I guess.
Right.
All right.
Just do it separately. Don't do all three.
Number 9. Use maximum deflection of a 10-inch by 14-inch.
Here, watch this.
Simple support of solar beam.
Wait, do it. Keep
And
it
then
up.
it's 15.
Did you get that one? Maybe.
Okay. 15 feet. 1,000 pounds per foot, uniform distribution.
10 by
Yeah,
big.
10 by 14, right? We're gonna assume the 14's straight up and down. And it's surface 4 sides. What's that mean? Because it says S4S. Anyone have a guess?
That means the planes are flat.
Means it's been surfaced on all 4 sides, so that means that this is not the true size. You have to look it up.
Always it happens.
Yeah, or sometimes it's, when you get big, it's not always a half, yeah. I think it is for a 10 by 14, but definitely gonna look at it.
Okay, is it good then?
This is number 9.
Yeah.
Allowable deflection is 1/300. Deflection allowable. So what is that? 15 times 12 is 180. 300 divide 0.6 inches.
Wait, what did you just do?
So the deflection allowable is 1/300 of the span,
15 divided by 300.
15 times 12 to get it in inches.
Oh,
Yeah.
okay.
On the final, we'll want to calculate the bending stress first. But we're just gonna do deflection right now. And on the final, I will say, check it in stress first. So that means check the bending stress before you calculate a deflection. Because if it's over the bending stress limit, there's no reason to do the deflection, like it's pointless, so. We're not doing that, because we're not in the real world, we're in academia right now, just calculating deflection. All right. What else is there? Redwood. That gives me an E value of something. I think we're good. What's the formula? For deflection. I think it's beam number one, right? Oh. I can't. Is it one?
Very first.
Yeah,
On
5WL to the fourth. Over what? 384. E.
Between.
What?
Since we have the max. Deformation or the max, stuff, could we switch around the equation and find the max load that it can take or not?
You actually, well. Yeah, so if you set it to this. Is that what you're saying?
Yeah.
Yeah, if you take the limit. And then it's a fun calculation, because what you're doing is trying to calculate W. But yeah, absolutely. Yeah.
I don't think I'm smart enough.
I mean, it wouldn't be. It's not the way to do this problem, because you're already given a load, you just calculate the deflection and see if it's within limits, but. All right, so it's 5, what's W? 1,000 pounds. Per foot. That's W. What's L? 15 feet. Gonna leave that in feet because I want those two to cancel. Oh, maybe I won't.
Quick question. The 1,000 pounds should be in the middle of the 15, so shouldn't that be like?
No, you don't concentrate it. You would concentrate it if you were trying to figure these out. Right? But for the equations in the back of the book, it wants W. And W is the distribution. That's a good question. All over 384 E for Redwood. Right, how much?
1,300.
1300, what's the unit?
Yes,
K
yes,
or PSI?
KSI.
Gibbs per inch squared. And then what's I? We'll look that up. 10 by 14. Ten by 14. I value is 1950 inches to the fourth. So we want inches in the end. Or feet, just know that you have feet, and then you could convert it. Either one's fine. But we have a lot of inches down here. We have feet here. So I might get rid of the 15. And put in 180. Right, that's a pretty easy move. And then I need to get this foot out of there. And I know that there's 12 inches per foot. I'm gonna write it that way so it crosses. So now I have pounds, whoops, I have kips down below, so I gotta get rid of one or the other. So I'll get rid of the kip. I know there's a 1 kip in 1,000 pounds. So that's a multiplier down in the denominator. Now I have pounds and pounds, those cross. I have inches to the 4th. One of those goes away. Looks like I have inches to the 3rd. Inches squared down below. That should leave me with inches. So that's the battle that all of these formulas have. Remember that 180 is to the 4th.
The 1,000 pounds be turned into 12,000 PSI.
It's not squared,
Okay.
right? It would be per inch if you did that, yeah.
The equation would run the same whether it's 1,000 or 12. It's just
It gets reduced by 12, so it's 1,000 divided by 12 to get it pounds per inch. Yeah. I get 0.45. Anyone get 0.45? What's the book get?
You need like a very large number,
Or is this? Yeah, no,
but there isn't, right? Okay, with the 12 right there, you're multiplying that though.
here?
Yeah.
No, it's dividing.
Oh,
It's in the denominator of the top.
uh,
So it's 5 times 1,000 times 180 times 4 divided by 12. That's
180 to the 4.
to the 4th. Yeah, to the 4th power.
0.449 is less than 0.6.
Yeah. Is that what you got?
I am getting a very large.
What are you getting?
What do you?
For
So
the, no, for
I
the
got
top.
a
That's
smaller
for the top.
number.
yeah, let's just calculate the top.
Oh, I get your number now, okay.
So the top is 437, 400. Oh man, it's got a lot of decimals. It's a big number on top.
I'm getting 4.37 E to the 11.
Yeah.
I was gonna
that's right.
say, it's
Oh,
3,
okay.
6, 9, 10, 11. 4.37. E to the 11. Yep,
Okay. So that's not.
4.37 e to the 11th on top.
So it'd be 1.3 million pounds. It'd be PSI for instead of kips. On the
I
bottom.
always get so much work up over it.
And down below, I get 9.7 3 e to the 11.
By 1,000, right?
All of it, 384 times 1,300 times 1,950 times 1,000. Yep. When you do this unit analysis thing or unit thing in the numerator's the top, denominator's the bottom, right? Yeah, in the numerator, all that equation is like its own little thing. And same with this, all this equation is its own little thing. So you just have to follow whatever you've done down here. And there's just no dividing down here. It's all just multiplication. This one is multiplication, this to the 4th, and then a division of 12.
For the bottom, I'm getting 7.2 D21. Am I doing something wrong?
Yeah, what are you taking? It's a 384
384
times,
1,300.
yep,
It's 950 to the 4th.
19.
1950. Sorry.
No, not to the 4th. It's just the unit.
Oh, that.
Just the unit, because it was an inertia that we calculated
Gotcha.
or looked up.
What'd you confirm?
I,
And syntax there, that's great.
Yeah, 19. I didn't get 1950.
I looked it up.
There
It's
we
in the
go.
table
1950.
for inertia.
Oh, I just copied it.
I calculated.
It so wrong.
Did you reduce these numbers?
To, what is it?
Oh, no, I didn't.
11, what is it?
Yeah, you gotta
9.5
reduce those.
by 13.
I don't know. You gotta look it up.
Oh, do you just have that?
Yeah, it's in the table. So you typically wouldn't calculate it if it's in the table. It is 9.5 by 13.5. But if you calculate it with the equation, it'll be slightly different than the table. But you don't have to, just look it up.
Oh, yeah.
Yeah. 1950. And that's the S4S thing. That's this. S4S means go to the back of the book. It means it's not really 10 by 14. It's 9.5 by 13.5. Because the timber industry is trying to be complicated. So only engineers can run the numbers and nobody else. Job security, so I'm glad they did it. We matched the book. That's scary. And it is definitely less than the 0.6, which is the 1/300th, so this thing is good. So on the final, if I ask you if the beam is safe or if the beam is good, and then I give you like limits of deflection, let's say, you can't just calculate it, you have to tell me it's good. And yet you should tell me why. Like this is good because that is less than that, right? So just kind of be descriptive test. If I say, explain.
In a real world setting, would you switch the equation around to find the load instead of the
No,
do this?
yeah, just do the analysis of what you have and then check the limits. Yeah. Yep. Now, I mean, there's situations where you're like this happened to me at Kiewit all the time. They wanted to build something, a trailer, a backhoe attachment, something, and they want to use the steel in the yard. The steel that we have, they just don't want to buy stuff. So then it's like, oh, I got a beam out there. I wonder how much that beam will carry. Then I have to calculate how much load will this thing carry. So there's situations, but not normally. Normally analysis, you're given everything and you just check the stress levels and the deflection and you're good before you're not. Cool. All right. Everybody did it? Just nod your head, yeah, okay, so then I'll just give you all points for it and you can keep it. Right, because I won't see you until we take the final. All right, the final. Comes from chapter 9. So it is like comprehensive, goes all the way back, which means there'll be some simple questions. Don't overcomplicate them. All right, so what is tensile stress? This is a review. Yeah, pulling something apart, right? What's the equation for it? P over A. What's compressive stress?
Stress speed.
Pushing down, what's the equation for it?
P over A.
P over A. Yeah. I'm gonna write it this way. What's shear stress?
What?
It's like their shear stress thing. It's like a T with a squiggly top.
Oh.
All right, what is it, Samuel? What's shear stress?
Like, when something's trying to shear.
Like, right? Or scissors. They're actually called shears.
It has something to do with the area that like,
Yeah, so what's the equation for it?
PLAE? No.
No, you don't get ahead of yourself. Just stick with, yep, P over A. But the A is different. The A is parallel to the load, where this is tensile stress of, we're pulling apart something. The load is perpendicular to the area, right? And same with compressive. Load is perpendicular to the area, but shear, like I'm gonna shear this thing off. The load is parallel to this area. Right? And the thing with shear, what was the tricky part about shear? Anyone remember? Like if you had a pin and it's got like connector here, and then this connector here is pulling this way. That's a bad drawing.
Like a connecting rod to a piston.
Yeah. It's all one piece here. Right, and we're pulling this out and that pin is gonna get sheared off. Right, if it fails. Anyone remember what the tricky part about that was? How many areas have to fail? 2. That has to fail and these 2 areas have to fail. So 2. So with shear, you have to think about what's gonna fail and how many areas will fail. That was the tricky part about shear. But shear can, it can come to you in a lot of different ways. Like you can have a block, right, that's glued to something. We've got glue in here and then we push on it. Right? So when we push on this block that's glued down, if it's gonna fail, what happens? It slides, right? The glue fails. That area down there is parallel to the load. That's a shear failure. What was this one? Bearing. We didn't do a lot of bearing stress. We did some.
that's like when something is like latched on to something, you can like pulls.
Okay, what's the failure look like?
It's like that.
Squishes. Yeah, it's like if you have a concrete block, right? And then you have a whole bunch of load on it and it's on soil. If this concrete block goes into the soil, it's bearing on it. It bears into it. Right? So what's the equation? Same old equation, P over A. If you have like a pin inside of a hole, So there's a pin, a hole, and then the hole over time looks like this. Right, because the pin has moved and it's literally squished the material. That's a bearing failure.
Right?
Absolutely. Yep. And then what about this one? Bending? Bending stress? Yeah, that one's kind of recent. MC over I. When something bends, we can calculate the bending stress. And then there was back to shear stress and beams. Right, that was VQ over IB. So these are actually the same stresses. This is a shear stress going on up here, but this is a shear stress in a beam. So that's pretty common in engineering where we're gonna have like this one symbol for multiple things. We just have to know and kind of categorize it in our head. Then there was stress concentrations. What was that? What concentrates or elevates the stress in a member?
When you put like a feature into it.
Yeah, like a hole.
Yeah.
Or I think the fillets, right, a reduced area kind of thing. Anyone remember the equation for this one?
KP over it.
Yeah, K P over A, good old P over A showing up. But the tricky part was K. Where'd we get that?
Oh, that garage.
That graph, yeah. So refresh yourself with that, yeah.
That'll be in the book.
Yep. Absolutely.
There's like R over D.
Yeah, the whole graph thing. And then there was something about A,
Area net.
area net. That's the leftover area. So if you pop a hole in something, you've reduced this area out of the cross section, right? So you have to calculate the area of the material that's left. Because that's what's going to carry the load, not the hole. The hole's a lack of area. So you have to calculate area net, and then you have to do the K factor, which is looking at the R to D ratio and calculating that, and then using the graph. So just refresh yourself on that. And then there was stress thermal. When do we get thermal stresses? Like when would we calculate them?
When it's outside. And then it's compressed.
You're close, I like it.
Temperature.
There's certain situations where we can have a temperature change, but we don't get any thermal stresses.
Fully or sheet, what's it called, steel beam?
If it's fixed,
Yeah, that,
if it's fixed. If it's fixed, in other words, it's not free to move. And the temperature goes up or down, we have thermal stresses. If it's free to expand, like the problem says, it's free to expand, or the problem shows you a pin and a roller means it's free to expand. Okay, then there's no thermal stresses. You would not calculate them, there is none. It's free to expand. The only time it's not, only time you do thermal stresses is when it's not free to expand or fixed. All right, what was that equation?
Alpha.
Yep,
Delta T.
delta T. Alpha is what? It's a great name.
coefficient of thermal expansion.
Yeah, it's a great party question, just so we know. Coefficient of thermal expansion, so that's it's a material property, right? Yeah. Copper has a specific thermal expansion, coefficient of thermal expansion. Wood has a specific, so this is a material property. What's E? Modulus elasticity, that is a material property, and that's the temperature change. Yeah. Now, if it is free to expand, like, hey, here's this thing sitting on the ground and the temperature goes up 800 degrees, that's hot. How much did it expand? Right? That is what they use for the symbol.
Delta thermal.
Did they?
I don't know, I think they use delta.
I feel like they used some Greek letter, like, oh, they did, they used this thing. I could never do it.
Lowercase delta.
Yeah. Yeah, and that's alpha L delta T.
What's the,
That's stretch.
Yeah, this is elongation. Very good. About this time, you're thinking, what, 10 questions? Gonna move you around, you can move you around a lot of different places.
10 questions.
Sure, I just upped it from 8.
what is our, what's our final schedule?
Tuesday, 1 o'clock. If that doesn't work, I need to know. Yeah, the final schedule has us on Thursday, but I want to do it Tuesday.
Here?
Yeah, 1 o'clock.
What is the latest we'll be here?
On when? I don't know. When's the earliest you can be here?
I don't know, because I'm
I'm gonna say the same thing. I don't know.
I have no idea until Friday. I'm gonna
Oh,
probably. that's Friday.
we'll talk Friday.
Okay.
We'll figure it out.
I have no idea what I should, because I have training.
Yeah, no, I get it. But as soon as you find out, let me know.
Definitely.
Yep. All right. What else did we do? Smoked.
I'm gonna do combining material.
So we did combine materials is not on the fund.
Wait, combined material, what do you mean?
Like if you have.
Maybe it should be on the fund.
If you have.
What?
It was in stress, yeah, it was in stress consideration. Yeah, where we calculated both stresses and a load.
Thank God.
Yeah, not gonna
It's
put it-
not.
not there. You,
Torsion,
we did torsion. What was that equation?
what,
TC
TC
over
over
G.
J.
Yeah, Torsion
Modulus
stress.
of rigidity. Oh, wait.
T,
Oh, that's for
C
angle.
over J. We didn't do a lot of it and my exam reflects what we did the most of. That's enough said about that.
So there's one problem on board.
If in. I'd make sure, honestly, now that you're kind of getting a list, I'd just make sure I knew where everything was in the book. So I don't have to spend time doing this, right? Just organize your book, you know?
Sticky note.
I would not encourage you to start going through homework problems and trying to find one that matches, because there are none, because mine don't match. I wouldn't write a test that way, that doesn't make sense. So, if you find yourself doing that, that's not a great strategy.
Interesting thing on torsion, has anybody brought in like a twist axle plate before? Yeah.
Yeah, I have one.
Get one off of retractor.
Oh, I remember that one, okay.
Okay, it's right there if you want to see it afterwards. All right, let's keep going. Now we're getting into like current stuff, right? So current stuff is chapter 13, where we actually did V and M, finding shear force and moment. So this is where students can really waste time. If I ask you to find the maximum shear force, that's all you have to do. But you're so trained to do shear diagram, moment diagram, all the points, you know, and everything else that some folks will do that. It just wastes time. So whatever the problem is asking for, that's all you have to do. And shear force is just finding the maximum shear force. That's shear diagram. And find the maximum value, be done, move on, right? So there can be a lot of noise in the problem, a lot of other things going on. That's not to trick you. That's just kind of real world. Like when you have to do something at work, guess what? Like the entire internet is right in front of you. So you can complicate things. So really just trying to look and see what you're supposed to do and do kind of thing. Yeah. 2 hours. 1 hour and 50 minutes. But I'm really not into timing them. So I have typically just let students go longer if you need more time to process things. You'll see people walking out of here in an hour, and then there'll be people here longer than 2 hours, but whatever, doesn't matter. More interested in what you know than how long it takes you to do something. And then, of course, the diagrams.
Is it a max force? And it's just like you get that from the diagram.
Yeah.
The biggest dot.
Yep. Yep, largest value, plus or minus, doesn't matter. Yep. Yeah, there's not many, I don't think, I haven't made it yet, so, but typically I don't have you do a start to end problem, that takes too long. So it could be pre-worked, like a bunch of stuff's already done, now just do this kind of thing. Or it can just be do a part, like checking in bending stress, that's it. So however you want to get there. Remember, you can get the moment, the maximum moment, if you can match it to one of the formulas in the back. There's moment equations in those formulas. So you wouldn't even have to draw the diagrams if you can match it. But it's got to match perfectly. Don't be doing that if it doesn't match. Right? But these formulas in the back, they have maximum moment right there, formula, and they have shear at any location. This does not have shear max. So it's not just deflection that's back here. It's max moment, it's moment at any location, it's shear at any location. It's telling you that R equals V. These resultants equal shear. So there's a lot of information there. But that's only if you can match it perfectly. It's kind of a shortcut, right? And the diagrams are there. Right? That's the shear diagram, that's the moment diagram. So use them. Formulas are there. And deflection. Again, we haven't done much. Questions? 8 to 10 problems. I haven't made it yet. Out of the 8 to 10, there'll be some super straightforward problems like 5-minute problems. So test taking strategy is to look for something easy and do it. That gives you a good vibration as a student. Don't just do the first problem. That could be the hardest one on the test. Kind of flip through it and go, oh, I can do this compressive stress thing really easy, right? Do something easy first. It just gets your mind going. If you have jitters, it gets rid of the jitters. It's a proven test taking thing. Keep track of your time. You don't want to leave a problem blank. If that's a 10, 15 point problem and you give me nothing, I got to give you 0 on that problem. That's huge. So you got to keep track of your time and get work done on every problem. If you find a problem is like sucking time, Move on, go away from that thing, come back to it. Okay? Supposed to get some sleep the night before. Like studying immediately before the test is really bad. It's just very not productive. Study the few days before the test, right, Todd?
What's that?
Study a few days before the test, not right before it. Right, Troy, is the correct
Right,
answer. Eat, right? Good nutrition. All that good stuff.
Sugar also helps.
Yeah, organize your stuff. That's probably the biggest thing I see that's a waste of time. Is students like spending time flipping through the book, trying to find that chapter. Or shuffling through their notes, like, because they're just unorganized.
What's wrong with tactile learning? Like making notes on pages, coloring things, like your mind just remembers things a lot better if you make it tactile.
So he leads me into extra credit, because I said there's extra credit on the final. If you create a crib sheet or a study document, and this is not just putting your homeworks together and stapling them, but you actually create a study document, that's worth 4 points extra credit out of 100-point test. But it's gotta be good, like everything we just covered's gotta be on there. And explanations of it, you know, little diagrams, whatever. So you can't just whip something up for the extra credit points. But that's a lot, you guys. Just saying, it's 4% of the final.
How much is the final of our final grade?
30%.
Not a lot.
It's a lot. It's easy money, is what it is. Easy money. And you definitely want to not show up. That definitely is not a good strategy.
Is there people that's gonna take it online or?
Nope, not that I'm aware of. Graceland will be here. Right, Graceland? Yeah, I heard her say, yep, she'll be here. All right, any other questions?
You'll put this on the document, right?
We're out of time. Yep.
Okay.